This is a separate videos. I want to talk about this Forrelation because this is not on the textbook. But I would say this is somehow like advanced application for the previous three algorithms like Cauchy-Jozsa, Berson-Vazirani, and Simons. Okay, so the idea is that this is defined by Aronson and some few others. Basically, previous three examples we discussed like only one Boolean function, right? So let's consider the two Boolean function f and g. And since we are working with phase oracle, so I can just assume it map to -1 and 1, right? So I just use phase oracle. And this is defined as Fourier defined as this. So you need to so f of x g of y -1 x dot y and the inner product and the sum over all the binary n Boolean n bit strings and with this. Okay, so the question so why this is called Fourier? This is somehow like the notation, the terminology, right? So Fourier transform, one can define a Fourier transform over f2 to the n by define f hat of y to be the following. So you can just, or I should say x, to be sum over bit string n bit string pn and -1 x dot y f of y and 1 over square root 2 to n. So you can view this is the you can view this is the definition of Fourier transformation over f in the f2 to the n sense. Okay, so you can see this basically the Hadamard, you just apply all the Hadamard here, right? So it's Hadamard you apply Hadamard on this f of y. Okay, so this is I can say this f hat is basically the Fourier transformation over f. So what this Fourier is basically asking is basically the Fourier plus correlation. Oh, so what this means is that I want to ask whether G and F whether G is a Fourier transformation of F. Okay, so I want to ask, let's say I want to ask what is F hat and G are close enough. Okay, so this is the intuition behind this. Okay, but how do you calculate these two, right? So basically this is inner product. I want to ask whether F hat and G are similar. So I can just calculate the following, right? I can just calculate the following, like sum over x, f hat and g hat, and then g, and then divide by 2 to the n. Okay, so you can see if g and f are the same, exactly the same, then this will be 1. Because now if they are exactly the same, then you will sum over 1, right? And the divide by 2 to the n is 1. And then since there are Boolean functions, so there are at -1 and 1, so this is indeed the inner product. One can check this is inner product is this guy is always bounded by 1. Okay, so if you plug this f hat of x and multiple g of x and sum over x, then you get this expression. Okay, so this is indeed just the inner product with f hats and g. Okay, the question is that I give you f and g where you can quantify how large this quantity is. Okay, so notice that for classical computing, it's very difficult to prove, but for classical computing, this is very difficult to compute, right? Because this is double exponential, right? You get not the double is 2 to the 2n. So you have like 4 to the n sum. You need to pick random. You need to pick x and y such that you get enough estimation of this object of this quantity. Okay. And in our case that we are focusing on the following two scenario. So I will first I promise so I promise the first case is that FGR pick random, FGR random. And the second case is that FG is very similar to the Fourier transformation of F. So the problem for you is to deciding either FG are random or they are the same. They are close. Okay, so indeed the circuit what we are going to use is that we cap with 2. So we Hadamard F, Hadamard G, and Hadamard. So there are just three layers. So you can see this is just similar as the previous algorithm, but with additional G and additional Hadamard. Okay, so I'm going to show you that the probability observation, the probability you get all z to the n will just be this phi absolute value squared. Okay, so this is what I want to show. And I also want to show that when FG are random, these are very small. When FG are correlated, this will be large. Okay, so this is the thing I want to prove. Okay, so I'll just tell you that the classical lower bound is very large. So the classical lower bound, you can check out this paper. I think is basically at least square root 2 to the n. So you indeed need exponential, but for quantum, then you just need one Curie. You just need to write this run this circuit, and you can get one. You can because this is negligible. This is some constant. So you only need constant degree. You only need constant Curies to get this. So this provide a maximal separation between quantum and classical. Because remember in the previous Simon's algorithm, in Simon's algorithm, right? Let's say so when one can compare with Simon's. So in the Simon's, that quantum just take there's a linear Curie, maybe that's a 10n, and the classical is 2 to the n divided by 2, right? So this is Simon's. This is exponential. This is linear. And I mentioned that if you can do non-classical measurement, then quantum can reduce to constant. But okay, but we don't have non-classical measurement, right? But in this for checking, the quantum is still exponential. Sorry, the classical is exponential, but the quantum has basically the constant. Because this is constant, this is negligible. Okay, so this is what I got to prove. Okay, so let's consider the following circuit. So this is 0 to n. This is F. This is Hn. This is G. Sorry. Yeah, it's train. And then we do a measurement. So remember the following identity. When you apply Hadamard to the x, you get 1 over square root to the n, summation of y minus x dot y. So this is the only identity that you need to remember. Okay, so this is 0 to the n. So when you apply this, then you get this 1 over square root to the n, summation y minus 1 x dot y. Okay, then you apply f here, right? You apply f, then you get f of y. So previously I used -1 to f of y, but now I shift f to be either plus or minus 1, so it's f of y. Now I apply this again. So I get 1 over 2 to the n summation y, and z, you need extra, right? You get -1 x dot y, f of y, -1 y, z. Good? Okay, now you apply g again, so you get extra g of z. So now we are already here. G of z. Okay, now you apply a final Hadamard again and you measure. Okay, so here, or maybe you here. So get 1 over 2 to the 3 and divided by 2 -1, let's say y, z, let's say. Oh, sorry. I did some stupid thing. Sorry about this. I'm stupid. Oh. What I want to say is the following. So this, sorry, I go too fast. So this one is indeed 1 over square root 2 to the n summation of x. So this guy, this guy here, is indeed here. This is indeed this one. Okay, so this is the output from f. Sorry, I'm stupid. So here is this. So this one is this 1 over square root 2n summation y minus 1 x dot y f of y y. Then I apply g of y. Sorry, this is x. Oh, this I'm stupid. Let me redo the calculation again. Stupid. So we start with 0n h f h g h. Okay, so read about it. So this one is all a linear combination. And this one is 1 over square root to the n x f of x and x. And this one is 1 over 2 to the n summation x f of x minus 1 x dot y y. And this one is with additional g of y. And finally, we apply another Hadamard again, right, on y. So we got 1 over 2 to the 3n divided by 2, summation of x, y, f of x minus 1x dot y and g of y and also z, right? There is extra z here, z minus 1 y dot z, z. Right, so this is the final state. Oh my God. Okay, it's the final state, right? So what's the probability that I get z to be 0? Which is I just plug z to be 0, right? So I get 1 over 2, 3n divided by 2, summation of x, y, right? So you don't care about z. So f of x minus 1 x dot y, g of y. So f of x minus 1 x dot y, g of y. We're in this and the square, so in this phi fg squared. Oh my God. Okay, so this is the proof. Okay, so when fg are random Boolean function, right? So let's say f and g are random Boolean function. So that means that you expect the overlap with f and g are very small. Okay, so you expect is very small. But notice the following. So notice that this probability of z equals 2 to the n is nothing special. So what I'm saying is that we already know that if we consider all the possible z, and the z from 0, 1 to 0, 1 and bit string, this is 1, right? This is the normalization condition. But if fg are random, there's no particular preference. So they are equally distribution, meaning that the probability of z equals 0, 1, 0, 2 to the 0 to the and bit string is 1 over 2 to the n. Okay, so it's negligible when n is large. It's negligible. Okay, but when fg are Fourierated or f has g hat, then obviously that this 5g is very close to 1. So that means that probability of z equals 0 to the n is very large, close to 1. Okay. Although this proof is not exactly 100% rigorous because somehow this f hat is not just a simple Boolean function, but we neglect some detail. If you want to see the true proof, you can go to see this paper. But yeah, the true proof is almost close to this. Just plot some concentration inequality in the paper. Okay, so what I want to say is that so when FG are random function, these are very small, right? But when FG are actually indeed the Fourier transformation between each other, then it will be very close to 1. Okay. And one can also define a more general. I can give you case function, and then you can ask what's the K Fourier. Okay. And you can consider all this. You get a very complicated expression, and also you can check there's a lower bound, upper bound. In a quantum, there's always one query to do this. Okay, so quantum can get you like very, very complicated patterns for these functions. And so this Forrelation method has two oracle, right? It has two so-called quantum oracle because you need query F and query G. But there's a new version that's called square Forrelation that one can actually compute the Forrelation, whether they are correlated by using the single query, single quantum query. Actually, you can indeed you can just query F using quantum query and plug output X and plug G of X. Okay. So the upshot is that you only you just need to remember this for sampling. This circuit is really important. Okay. And I already give you a hint that this is indeed Fourier transformation. So once if you know some group representation, then you know what's the meaning of the Fourier transformation over a finite group. Then it's very easy for you to understand at least the meaning of this quantity. Okay, so yeah, that's it. That's for that. So this is hopefully this PowerPoint give you the full interesting quantum algorithm and give you some idea that how these Hadamard transformation are powerful. Okay, see you.